All right, section 1.2 is called Exploration with Patterns. And we kind of started looking a little bit at some pattern kind of things with Gauss and his method and such in the last section. But we're going to look a little bit more with patterns and doing some different kinds of things with them. The first thing we're going to talk about is a little bit of vocabulary so that we're all on the same page. The first word on here is the word conjecture. A conjecture is a statement or a conclusion that has not been proven. It's your guess as to what's happening. That's all it is. Now, it's usually an educated guess. We talked a little bit about educated guessing in the last section and how random guessing is probably not especially helpful. But it's a conjecture. It's a statement or, it's something that you're saying, this is the way it is, but you haven't proven that it's true. Okay, that's a conjecture. There's two types of reasoning. There's inductive reasoning and there's deductive reasoning. And they are similar, but sort of in reverse. Inductive reasoning is reasoning that takes that makes generalizations based on observations or patterns. For example, if you had 3 days in a row where the temperature was 55 degrees and you're on day 4, your conjecture might be that tomorrow it will be 55 degrees as well. Okay, so you take something that sort of you've observed this happen numerous times and you believe that this is going to happen next. This is basically what people use when they use, for example, I had somebody, people don't always like using your ACT scores or your high school GPA or whatever to put you into classes, okay? So we always have somebody who's like, but I can do so much better, I don't do well taking tests. Well, it's an inductive reasoning. Basically, we're saying that we've looked in the past at people who've had ACT scores of fill in the blank, and if it's above this certain level, they're successful by and large on the on this class, and if it's below this level, they're not. Okay, so we're making a generalization based on specific cases. Deductive reasoning is the other way around. Deductive reasoning usually takes something like mathematical axioms, theorems, or definitions, undefined terms, and they use it to prove something else. So anytime that you're given an equation and you're told, now figure out what in the world is y when you're given this x value, that's using deductive reasoning. And I'm going to show you how we're going to use it in a minute, and it'll start to make a little bit more sense. And the last thing here says counterexample, and a counterexample is an example that proves that something's false. Okay? A counterexample is simply an example showing that something doesn't work. And there's always that example. My brother-in-law, he is a dentist. He's not a dentist now. He's a maxillofacial surgeon, actually. And he is a downright counterexample to any claim you'd ever want to make about somebody's success in high school predicting future success. He was a 12 on his ACT. Seriously. 12 on his ACT. And he is a doctor in the Air Force. Like, that's like a counterexample if I've ever heard of one, right? I mean, like, that's just not supposed to happen. His ACT would have said that he was predicted to be a bum or something. I don't know what. Probably wouldn't even told him he could do that. I don't know. I mean, like, that's just not normal, right? Okay, so a counterexample is just something that shows something else is not going to work. All right, we're going to talk about sequences. A sequence is simply an ordered arrangement of numbers, figures, or objects. Kids start working with sequences in preschool. And they usually start working with preschool sequences in something like this. It goes circle, triangle, what comes next? You guys know what I'm talking about? Or you see red square, blue circle, what comes next? So they're looking at kind of two patterns at the same time. So we start looking at patterns of objects, which are called sequences, with objects usually first. Now what we're going to look at is it as you progress in mathematics, you start looking at sequences of numbers, predicting what kind of a number would come next. And this idea of predicting things is a very big component of mathematics. And it's used, at various, in various degrees in lots of professions. So one kind of a sequence in particular is called an arithmetic sequence. And an arithmetic sequence is a sequence where you look for the next term based on what the previous terms were, and there's some kind of a common number added or subtracted to get the next term. And so I'm just going to write a very simple one down that we've seen twice today already as you guys have asked me questions about things. I'm going to write it as a sequence, which means it has commas between it. We looked at it with pluses between it. But when you had this sequence, even if I stopped right there, you know what comes next, right? It's the number 11, because the number that you're using to get from one number to the next is a common value. What are you doing? You're really just adding 2 every time, right? So this number that we're adding is called the common difference. It's the value that gets added. And there's nothing special about being plus 2. We could subtract 2 every time and have the same thing. It'd still be an arithmetic sequence. Okay, so we're adding or we're subtracting the same number to get the next term. All right, a recursive formula is a formula based on the pattern established after one or more consecutive terms are given. It's a rule that shows how to obtain a term from a previous term. So what I just described before, where I said we add 2, that's a verbal description of a recursive formula, but I had to actually know where to start, right? Like I gave you the first couple of terms in that, I gave you the first several, and then you could continue the pattern. But if I said the pattern is add 2, well, you wouldn't be able to tell me the sequence unless I told you a number in it, right? I mean, I actually have to tell you, hey, it starts with the number 7, and then you could do it. So recursive formula is just that. You have to have a value in the sequence, and then you have to know how you continue the sequence after that value, right? An nth term formula, or this is sometimes called a general term, or a general formula, is a formula used to find the nth term no matter if you're given the terms or not. So it looks more like an equation is what it looks like. Okay, so it looks like you've got an equation, you're asked to find what is term number 5, and you plug in a number 5 in for a variable, and then you're able to tell me what the 5th term is. But you didn't need to know what the 4th term and the 3rd term and the 2nd term and the 1st term were to do that. Does that make sense? All right, so there's one more that's here, and this is not a arithmetic sequence, but I want you to be aware of it because it occurs very frequently in nature. Does anybody know how to say this guy's name? Fibonacci. Excellent, Fibonacci. This is a Fibonacci sequence, so you guys must have seen his name or seen this sequence before. Do you remember how it is that you move and find the next term in this sequence? Right, you add the previous 2 terms together. So let's just take 2 terms in order, 3 and 5. If we add 3 and 5, we get 8, which is the next term. So let's write a couple more of these down. What would come after the 21? 34 is right, because we would add 13 plus 21. We'll do one more. What would come after 34? 55. Okay, so one of the reasons I put this in here is because I don't want you to think that things are always arithmetic, and we're going to have one more option here in a minute. They're not. I mean, there's other ways to get sequences, and there's other ways to see patterns and numbers besides just adding one number and getting the next term, okay? So Fibonacci sequence is one of those patterns, and you'll see a couple more of them, I think, in your homework. All right, another type of sequence is called a geometric sequence. Now, the difference between the geometric sequence and the arithmetic sequence is the operation that you use. With arithmetic, we added or subtracted a number to get the next term, right? With geometric, we multiply or divide to get the next term. That's the only difference. It's the operation that we're doing. So, for example, we might have this sequence. How am I getting from one term to the next? Yeah, you're multiplying by 3. Now, let me make it a little bit more complicated. Let's say instead we had, I don't want 1. We'll start with 2. Let's go with that one. And it keeps going. Yes. So it doesn't actually have to start with a number that I was using. Sorry, that was what I was trying to avoid. So the way I get from 2 to 10, one way to do it would be to add 8. But that's not helpful because it doesn't work for the next term. Another way to do it would be to multiply by 5. And sure enough, if I multiply by 5, I get the next term. I think I did them okay to get the next term 5. That's what happens when you make stuff up on the spot. It doesn't always work, but I think I did it okay this time. Did it work? Yeah. All right, this term that we multiply by, and it works for division too. We could divide by a number to get the next term. The term that we multiply by is called the common ratio. When we add and subtract, the term is called the common difference. Okay? We're going to see the use of this in a minute. I know it feels like a very awkward thing to be placed in the middle of what we just did, but I'm going to use it here in a second. So this is the definition of an exponent. When we have a raised to the power of n, we call it an exponent. N would be a natural number. Now, natural numbers are the numbers you naturally learn to count with when you're very tiny. What's the first number you learn to count with? Where do we start? You start with the number 1, right? Is that the smallest number? No, but it's the smallest number that we learn to count with when we're like 3 or 2 or whatever it is, whenever the little ones start counting. So natural numbers are the numbers 1, 2, 3, 4. It's the counting numbers, because that's what this is talking about. So we're looking at putting numbers in that place where the n is as natural numbers. So if we had something like a to the 5th, it would mean that we have a multiplied by itself 5 times. And so down here in my description, this should say n times. Right? So a to the n would be a multiplied by itself n times. For now, we're going to take it as a definition that if we had a 0 exponent, that it would be the value 1. Okay? I will tell you that I will be happy to prove that for you, like really prove it, not just conjecture that it works, but really prove it in Math 2. But we need some properties of rational numbers to do that, and we don't do rational numbers in Math 1. Okay? So for now, we're going to say that this is just a property that we're going to take as truth. Okay? So anytime you have a power of 0, then we get a quantity of 1. Okay, so what we're going to do is we're going to take a list of numbers, 1, 4, 7, 10, and we're going to do a couple of things. The first thing it says is that we're going to list the 3 terms that continue the sequence. So we're going to find what are the next 3 terms. So this is like problem number 1. Problem number 2, and we don't necessarily have to do it in this order, is that we're going to decide if it's arithmetic or geometric, and we are going to recognize that it could be neither. So if that if that's an option, when you're doing your homework, neither is perfectly a valid thing to look at as well. We're actually going to do one more thing that's not written here because there is a question or 2 in your homework that asks you to do this. We're going to find the nth term, or that's sometimes called the general term, so that you know how to do that as well. So I recognize it's not in your directions on this particular one. Add it in there like it was supposed to be. All right, so looking at the first one, 1, 4, 7, 10, how are we getting between the numbers? Add 3. All right, so we're going to do this like all out of order. I am adding 3. So the recursive sort of description is add 3. So if I'm adding 3, does that make it arithmetic or geometric? Arithmetic. So I'm going to do out of order. This is the second thing it asked me to find, and I'm finding it first because I'm a rebel today. Okay, I'm arithmetic. All right, so what would the next term be after 10 then? 13, and then excellent. So so far what I'm boxing in are the 2 answers that we have. Arithmetic and 13, 16, 19. I'm going to show you how to create an equation or a formula based on this information. Now, I want to give you a disclaimer at first. I could just give you a formula and we could put numbers in. But you guys heard me say just a minute ago about this other problem on the board, and I said it's really not such a good plan to just memorize formulas because you tend to forget them. And the other problem is that if you didn't know how they worked, you're probably not going to remember them, or if you remember them, you're probably going to remember them wrong. And those are all problems. I'd rather you understand why the formula comes from where it comes from, and it's not a difficult process, I promise. So I just want you to recognize that when you look in the book and you find a formula for doing this, I'm perfectly aware that there's a formula, okay? And I'm purposely not showing you the formula because I don't find it to be especially helpful in terms of understanding. So here's what I do want you to recognize. We are adding 3 lots and lots of times, right? That's what this whole thing is. So instead of adding 3, so if you wanted to do 3 plus 3, ignore the numbers I'm given, 1, 4, 7, 10. Ignore that for the moment. If I just told you I want you to add 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3, you're going to add 3 16 times. You're probably not going to get your calculator out and really add 3 16 times, or even by hand. You're not going to do that. What are you going to do? You're going to multiply, because that's what this is. Repeated addition is really multiplication. So my formula that I'm about to write down is going to start out with 3 times n, or you can just write the 3 and the n next to each other. They don't have to be. Because multiplication really is just repeated addition, and if we have an arithmetic sequence, that's what it is. It's repeated addition. Agreed? Okay, now the problem is that if I plugged in the number n equal to 1, n equal to 2, n equal to 3, it does not give me 1, 4, 7, 10. And that obviously is a problem because I'm trying to get an equation that's going to give me 1, 4, 7, 10. Right? So what we're going to do is we're going to basically like test a point. And the point we're always going to test, this is the cool thing, is n equal to 1. Okay, so here's what I want you to do. I want you to plug 1 into 3 times n. And what do you get? You get 3. But you're supposed to be getting the number 1, actually, because we're going to call this term n equal to 1 for our first term. This is going to be n equal to 2, n equal to 3. So we should be getting the number 1. And we're getting the number 3. So you know how we fix that? We subtract 2. You got it. So my formula isn't really supposed to be 3n. It's supposed to be 3n minus 2. And if you aren't sure if you did it right, the cool thing is you just test another value for n. So now why don't you test n equal to 2? What happens when you plug in 2 into this equation? You get 4, right? Is that your n equal to 2 or your second term? Sure is. And you could test all of them if you really wanted to, but I assure you they're all going to work now that we've got the first one in there right. So the general term here, the nth term, is 3n minus 2. Okay, so let me run back through the process of what we did to get there, because we did a few things. The first thing we did is we recognized that it was arithmetic. Arithmetic means I add a number multiple times, okay? So we're recognizing, okay, well, adding something multiple times is really just multiplication. It's multiplication by that common difference, the one that I keep adding together, which was the 3. So I take the 3 times n because that's multiplication, okay? And then I test the first point. And there's nothing special about the first point. It's just that I like plugging in 1. Come on, be honest here, right? Plugging in 1's easy. You plug in something else and it's going to take you maybe not a lot more work, but some more work. Okay, so I plugged in the number 1. And I said, okay, when I plug in the number 1, I don't get the first term. If I did, I'd be done. And that'd be great too. We could be done. I mean, if it worked, it worked. Great, you got it, okay? But if it doesn't work, what you do is you say, okay, well, what would I need to add or subtract to actually make it work? Well, in this case, I need to subtract 2 or add 2 or whatever we've got. So I think we wrote down subtract and I think we meant to say add. Did we? Yeah, I think so too. Okay, sorry about that. I was probably something that was spelled wrong. Yes? No, was it subtract? Oh, I was thinking 4. We started at 1. You're right. Goodness, that's what happens when you keep talking. All right, yes. Okay, so we subtracted 2 to get back to the number 1 because the number 1 was the starting number. Yeah. Okay. Let's try another one. Take a look at the next one. How do I get between terms on this one? Multiply by 2. So that's the recursive relationship. It's times 2. So is this arithmetic or geometric? That makes it geometric. All right, so let's continue that pattern. What would come next? 48, 96, 192. Very good. Some of you are really good at multiplying by 2. It gets big really quick when you use multiplication. So here, let me just warn you that there's a few of them in your book that they're going to get so big so quick that your calculator's not going to be able to handle the kind of numbers you get. It's going to happen. So just write down what your calculator shows. If you're concerned when you get to that point, we'll talk about it in class, okay? With multiplication, the numbers get big quickly. All right. So we've found that it's geometric. We've found the next 3 terms. The next thing we're going to do is we're going to find the general term. This general term doesn't work quite the same way because multiplying by a number a lot of times is not multiplication. So think with me for a moment. If I wanted to do 2 times 2 times 2 times 2 times 2, a whole bunch of times, what's an easier way of doing that? Exponents. It's exponents. It's 2 raised to a power. Right? So we're going to use exponents. And the base is going to be a 2 because that's the number that's multiplied by, on this one anyway, multiple times. So we have 2 to an exponent. Now, I'm going to tell you that the exponent that we need is n minus 1, and I'm going to tell you why that works. Okay? So go ahead and write down that the exponent's n minus 1 and not n. Let's say for a moment that we had the sequence. I'm not going to use the one I've got. I'm just going to use the sequence that starts with the number 1, rather. 1, 2, 4, 8, and so forth. So my sequence is going to start with the number 1 here, okay? If I put in that my sequence is simply 2 to the n, I know I'm like all over the screen now. Let's just say we had 2 to the n. If I put in n equal to 1, it should give me the first term. But if I put in n equal to 1 in here, what is 2 to the 1 power? It's 2, so it doesn't actually give me the first term, it gives me the second term. So if the exponent is left as the exponent n, it gives you the second term instead of the first term. That's really what happens. So when I'm subtracting by the 1 right here, it's because I don't want it to give me the second term, I want it to give me one term less than that. So that gives me my first term. Okay? You can simply remember that the exponent is always n minus 1, and that's okay, but the reason is because this actually causes it to reset to being the first term and the second term. All right, so let's go back to our actual problem, though, because our actual problem doesn't start at 1 or 2. It starts at 3, which is not going to work with 2 to the power. I mean, like, that's going to give me a bunch of things that are even. So what do? Well, what we do is we simply multiply by 3, because I should be getting things that are multiplied by 3. Let me show you with the numbers that are actually here so you can see why this works. This number is really 3 times 1. This one is 3 times 2. This one is 3 times 4. This one is 3 times 8. Do you see these numbers? 1, 2, 4, 8. I think they're the ones I just erased. Those are powers of 2, aren't they? And all of those powers of 2 are multiplied by the number 3, right? The 3 that's in front of them, right here. So the reality is that this number right here just comes from what is the first number in my sequence. Whatever it is gets multiplied by it. It's the number 3. So if my sequence had not started out with 3 and it started out with 5, I'd be multiplying everything by the number 5. If the sequence started out with 8, I'd be multiplying everything by 8. That's how we do that. So this term right here is just coming from the first term. N is the term number you're on. In all of these cases, my N is representing my term number. So if I'm on the first term, it's N equal to 1. If I'm on the second term, it's N equal to 2.
So the N minus 1 will never change, but the 3 and the 2 can change?
Exactly.
Okay.
Yeah, the N minus 1 will always be the same. The 3, that location is just always whatever your first term is. And the 2 is the common ratio. It's the number that we keep multiplying by. Okay? All right, so this part right here, part C, says, is it inductive or deductive reasoning? So flip back to the first page of your notes to remember which one was which. Inductive reasoning takes specific examples and creates a general conclusion. Okay? Deductive reasoning takes a general statement and creates specific examples. What did we do on this?
We took specific examples and created general.
Right. We took specific examples and we tried to generalize what was happening for the rest of what was going to happen, you know, in this situation. So is this inductive reasoning or deductive? It's inductive reasoning. It's taking specific examples and predicting what's going to happen next. I mean, this is what happens in life all the time. Usually is inductive reasoning. Why do we think the world's going to end? Because global warming indicates that whatever. You know, why do we think that? Why do we think it's going to be cold in the winter? Because we live in Oklahoma and it's colder in the winter, right? I mean, like, this is a pattern that we've noticed over time and we predict that it's going to happen again, kind of thing. All right. Next one, example 2, says that it wants us to find the first 5 terms in the sequence with the nth terms as follows. So these are our nth term formulas. So we are being given the nth term that we worked so hard in the last examples to find, right? We're actually given that part of it this time and we're asked to create the sequence. Okay? So if we've got the terms, general term or the nth term 5n plus 6, we can find the first term by doing what? Plugging in 1. So if I plug in the number 1 into 5n plus 6, what do I get? I get 11. right? So I'm doing n equal to 1, and I get 11. What would I do to get the next one? Yeah, I'd put in n equal to 2. If I put in n equal to 2, what do I get? 16. What if I put in n equal to 3? 21. We're going to do one more, and then I'm going to make you do something different on the last term. What are we going to do to get the next one? Plug in n equal to 4. So what happens when I put in n equal to 4? 26. So I want you to pause for a second and tell me, what do you think the next one is without plugging in n equal to 5? 31. Did you see a pattern? What's the pattern?
1, 6, 1, 6, 1, 6, 1.
Okay, good.
1, 1, 2, 2.
Plus 5.
The pattern's actually plus 5. That's what's getting you the 1, 6, 1, 6 pattern at the end of the numbers. We're adding 5 every time. Do you see it? Yeah. This is plus 5. Now I want you to look back at the equation and tell me why is the pattern plus 5? Because it's 5n. That's what the 5 in the number 5 times n does. Is it progressively adds 5 to the number as it sort of, ticks to the next piece of that. All right, so if I'm adding 5 every time, is this arithmetic, geometric, or neither? It's arithmetic. Arithmetic is a sequence where the same number is added every time to get the next term. So this one's arithmetic. All right, let's take a look at the next one. N squared minus 1. So if I put in n equal to 1, what do I get? 0. What about n equal to 2? 3. What about n equal to 3? 8. How about n equal to 4? 15's correct. And n equal to 5? 24. Okay, so that's the first thing I was asked to do, is to simply find the pattern, right? Not to find the pattern, but find the first 5 terms. Now let's examine the pattern, because the pattern tells us whether or not we have something that's arithmetic or geometric, or neither, okay? So if I look at the pattern, the first thing that we're wanting to look at is, or at least one of the things we could look at is, could I add something multiple times and make something work? So if I were to try to do that, I want to actually write this out so I can show you something else in a minute here. Let's say I wanted to add, what would I have to add to get from 0 to 3? 3. How about 3 to 8? 5. 8, 7, 9. Now, that is not the same number every time, agreed? But do you see a pattern in the addition? There's a pattern there that actually would be quite helpful. So if I didn't have this equation, could I predict what the next term should be? What would I have to do? Add 11. So this is not arithmetic, right? Because arithmetic, it should be the same number every time, but there's definitely a pattern. Agreed? Okay. Let's double check real quick, and this is a real quick thing. Is it geometric? No. The fact that there's a 0 in the sequence means it can't be geometric. Flat out. Why? 0 times anything is 0. I can't multiply that very first term 0 by anything to get 3. It's just flat out not possible. So we said it's not arithmetic, it's not geometric, so it's neither. I do want to show you one cool thing about this, and I want you to sort of star this and draw an arrow to it because it's going to be helpful in your homework later. There's a pattern here, like we said. It's not arithmetic, it's not geometric, but I want you to see something real cool. I want to find the pattern between these numbers right here. I add 2 each time, right? So the first time I tried it, it was not arithmetic, but when I looked at the numbers that it created when I tried it, that one was arithmetic. These have a name. This right here, when we look for the number that we add every time, is called the first differences. Right? First, because it's the first time I do it. Differences, because the equivalent of addition, of what do I need to add, is that I subtract the numbers, is what we're really doing. How do we know to get from 0 to 3? We add 3 because 3 minus 0 is 3. I mean, that's what you're doing. You're doing it first differences. So what do you think the second time is going to be called? Yeah, it is. It's second differences. And if I had to do it a third time, third differences. So there's a couple of problems in your homework where they're not arithmetic, they're not geometric, but you can do this sort of a repeating process of looking at what the differences are, and eventually you do actually end up with something that works out to being one of the differences further down, like the third differences is actually arithmetic, or the fourth differences is actually arithmetic. And that's helpful because you can then find a pattern when it didn't look like a pattern existed to begin with.
Do you want us to do that or just say?
Well, it'll have different directions. It'll say something like find the next three terms. And it will be neither, but without recognizing what the pattern is, it's really difficult to find the next three terms. So you might have to do a couple layers of these differences to figure out what kind of pattern you're actually seeing. So that's why I mentioned it. Now, this question, part C, inductive or deductive? This is deductive. Why? Yeah. You're starting out with an equation or a formula, a general rule, and you're finding specific examples for something. Right? Yeah. All right. I think that's a fantastic place to stop. How about you guys? Okay.